Hello guys, welcome to the course P block elements. We are discussing the group 15 elements and today we are going to talk about the chemical properties of the group 15 elements, or you can say the various trends that we are going to see in the reactivity of the group 15 elements. So today we will be talking about the reactivity of the group 15 elements in general, and then we will be discussing in detail the reactivity towards hydrogen, or you can say we are going to discuss today about the hydrides of the group 15 elements. Very essential it is going to be that you have watched the previous lecture where we talked about the oxidation states of the group 15 elements, because that is very important in the understanding of all the chemical properties. All right, so I hope you have watched the previous lecture. In fact, you've watched all the previous lectures before viewing this one. I am Dr. Ritu, your educator from the channel H2O, the A to Z of chemistry, and I hope you're going to enjoy your learning with me. My only request, please do watch the lecture till the end. We are going to discuss today very important things. It is going to be a detailed discussion of each and every small little concept which can be asked in the examination. Also, I'm going to be discussing with you very important previous year questions from this topic. So please do watch the lecture till the end, and I am sure that you will not regret your decision. So let us begin the learning. So as we begin with the discussion in the trends in the chemical properties of the nitrogen family, the first important thing that we will be discussing today is going to be the reactivity. And here chiefly we will be talking about nitrogen and phosphorus only, because these are the two elements of the group 15 which are going to be very important for our understanding. Wherever else we will be requiring to seeing the trends for all the group 15 elements, we will be seeing that also. All right, so as we talk about the reactivity, first we will be discussing nitrogen. So nitrogen, you all know, this is a diatomic gas. It is present in the atmosphere. So we have talked about this in the atomic as well as in the physical properties also. So nitrogen, this is inert at room temperature. It does not react. Okay, and this is a diatomic gas and it has a presence of a nitrogen triple bond. So now why a nitrogen triple bond is present in case of the nitrogen molecule? This is because nitrogen, this has a very small size, it has high electronegativity, and because of these it is possible for nitrogen to form a effective p-pi overlapping, and hence we see the formation of multiple p-pi bonds in case of nitrogen. Okay, and as we are going to go down the group, the size is going to increase, the electronegativity is going to decrease, and the effective overlapping of the p orbitals is not going to be possible. That is why we see this multiple p-pi bonding only in case of nitrogen. And as a result of this, the nitrogen molecule will be having a very short bond length of 1.094 Armstrong. You need not remember the values, only the understanding of the concept is going to be important. So why it has a short bond length? Because of the presence of a nitrogen triple bond. And also because of the presence of a nitrogen triple bond, there is going to be very high bond dissociation energy of 900 kilojoules per mole. So breaking one bond requires less energy, breaking two bonds requires more energy, and breaking three bonds is going to require a lot of energy. So that means it is going to have a high dissociation energy. All right. Now nitrogen, this can dissociate at a higher temperature and then it is going to become reactive. So when is nitrogen going to react with other substances? When it is going to attain a higher temperature. Now this inertness of nitrogen, this is very beneficial to us also. Why? Well, this is because it dilutes the effect of atmospheric oxygen. You all know that in air we have 78% as nitrogen, and 21% as oxygen. So it is 1/3 oxygen and 2/3 of nitrogen. So it is diluting the effect of atmospheric oxygen. And why do we need that dilution? It is because oxygen is responsible for combustion as well. It is responsible for rusting. So every substance, if it is going to be excess of oxygen, it is going to be burning a lot, and then we will not be able to control that burning. Similarly, rusting also happens in place of in presence of atmospheric oxygen. So this rusting could not be stopped. This burning could not be stopped because of the atmospheric oxygen had nitrogen not been present in the atmosphere. Okay, so now you understand what is the importance of this inertness of nitrogen. Nitrogen is not reacting with oxygen also. Had it been reacting with the oxygen at the room temperature, there would have been the formation of nitrogen oxides, which are going to be very harmful for us. So this is really very helpful that nitrogen is an inert gas. So the next we have is phosphorus. So phosphorus, this is quite reactive as compared to nitrogen. Why? Because nitrogen, this exists as a nitrogen triple bond, a diatomic molecule, whereas phosphorus, this is going to exist as P4 with each phosphorus atom making 4 covalent bonds with other phosphorus atoms. Okay, so we find that here in the case of nitrogen, it is going to be multiple P pi bonds they are formed. So obviously the bond dissociation enthalpy is going to be high. You have to make 1 bond, 2 bond, 3 bond. But in case of phosphorus, between 2 phosphorus atoms, there is just 1 single bond. And therefore, the bond dissociation enthalpy, this is not going to be that high. And we find that phosphorus, this is quite reactive as compared to nitrogen. But one very important thing that you have to remember over here is that if we compare a single bond, a nitrogen single bond and a phosphorus single bond, then in that case the nitrogen single bond is going to be weaker than the phosphorus single bond, because in case of nitrogen, the nitrogen atom, this was small, right? And when it is formed a bond with another nitrogen atom, the bond length is going to be less. And there are going to be high interelectronic repulsions between the non-bonding electrons. Okay, so the electrons, they are going to be repelling each other, and hence the single bond is not going to be that stable. It is going to be weak and it can be broken easily. But the bond dissociation enthalpy in case of the nitrogen molecule is more than in the case of the phosphorus molecule, because here it is not a single bond that is present. Here between the two atoms there are 3 bonds present. Okay, so I hope this will be clear, and this is going to be important. In fact, this is one of the parts of a question which has been asked for the IIT examination. I will be showing you the question also at the end in the lecture review questions. So the next topic that we have to discuss today in the trends in chemical reactivities is going to be the reactivity of the group 15 elements towards hydrogen, or we can say that we are going to understand about the hydride formation, and the hydrides, they are going to be having the general formula MH3. So what does this mean? M is going to be the group 15 element, and we will be having over here the group 15 element in the -3 oxidation state. Hydrogen will be +1. So +1 into 3 is going to be +3, and the group 15 element, this will be in the -3 oxidation state. So I hope you all remember from the lecture on oxidation state, which was the last lecture that we discussed, that all the group 15 elements, they can exist in the -3 oxidation state, but the tendency to exist in the -3 oxidation state is going to decrease down the group. Why does that decrease down the group? Because again the size is going to increase, the electronegativity is going to decrease, therefore the electron gaining tendency is going to decrease down the group. This is what we have learned in the previous lecture. All right, so building upon that, we are going to understand today about the hydrides. So all the elements of the group 15, they are going to form hydrides because all of them, they can exist in the -3 oxidation state. So we will be talking today about, first of all, the structure of these hydrides. Then we will be talking how various reactions, these hydrides, they are formed, although we will not be going into the details many of that, because we have to anyways talk about ammonia, which is the hydride of nitrogen, and we have to talk about phosphine, which is going to be the hydride of phosphorus in detail in the upcoming lectures. Okay, so we will be just briefly talking about how these hydrides they are formed, and then we are going to be talking about the characteristics of these hydrides. So it is going to be very important discussion, so please be very attentive. So first thing that we will be talking about is going to be the structure of these hydrides, and I will begin the discussion with the structure of the ammonia molecule, which is going to be the first hydride, the hydride of nitrogen. Okay. So because you all have studied about this in chemical bonding, so this should not be very easy for you. First of all, we have the electronic configuration of nitrogen, a baby's task for you people now. So nitrogen, this has the atomic number 7. So it has 7 electrons. The configuration is going to be 1s2, 2s2, 2px1, 2py1, 2pz1. I hope no problem. Now, when it is going to be forming the ammonia molecule, what will be happening is that these 4 orbitals of the valence shell, they will be undergoing hybridization, and when they will be going hybridization, what will be forming? Well, they are going to result in the formation of 4 hybrid orbitals, and these are going to be sp3 hybridized orbitals. Okay, I hope this is clear. No problem. Good. So now what do we have? We have 4 hybrid orbitals. So just let us draw those 4 hybrid orbitals, and those 4 hybrid orbitals, they have to contain how many electrons? They have to contain 5 electrons. So as a result, what will be happening is, first of all, they will all be singly filled. Okay. And then one of them, it has to be doubly occupied. So this doubly occupied is going to be the one which has a lone pair. And these half-filled orbitals, they are the ones which will be participating in bond formation with the 3 hydrogen atoms. Okay, so I hope this is clear. So we have the nitrogen atom to be sp3 hybridized with 1 hybrid orbital being occupied by the lone pair, and the 3 other ones, they will be participating in bond formation with hydrogen. So as a result, what type of orbitals which are going to be involved in the formation of the nitrogen hydrogen bond? For nitrogen, it is going to be sp3 hybridized orbital, and for hydrogen, it is going to be the s orbital. So they are going to overlap to form this sigma bond. Okay. Now, what about the geometry of this molecule? We have 1 lone pair of electrons and 3 bonded pair of electrons. So according to the VSEPR theory, what is going to be the geometry? It is going to be a tetrahedral geometry. So the nitrogen atom in ammonia is surrounded by 3 bonded pairs and 1 lone pair directed towards the 4 corners of a tetrahedron. So it is going to be what geometry? It is going to be a tetrahedral geometry. Okay, and what about the shape of the molecule? Well, the shape is going to be a distorted tetrahedral or a pyramidal shape. Why? Because of the presence of a lone pair. Had it been all bonded pair of electrons, the shape would have been a tetrahedral shape. But now because a lone pair is present, so and we know that a lone pair bond pair repulsion is going to be more than a bond pair repulsion. So these are going to come closer, and hence we will be seeing that the bond angle is going to reduce. For a regular tetrahedral geometry, the angle is going to be 109.5, which we see in the case of the methane molecule. But now because of the presence of 1 lone pair, this bond angle is going to reduce from 109.5 to approximately 107 degree, or the exact value is going to be 107.8 degrees. Okay, so this is because of what? Bond pair lone pair repulsion is going to be more than the bonded pair repulsions. Okay, I hope this is clear. Good. So now this we can generalize the structure of ammonia into the structure of all the hydrides. So if the central atom is going to be M, a group 15 element, all the group 15 element hydrides, they will be having the central atom M to be sp3 hybridized. There will be 4 sp3 hybrid orbitals, and one of them will be containing a lone pair, just like we did for ammonia. And then the geometry is also going to be just similar to that of ammonia. All of them, they will be having a tetrahedral geometry, but the shape is going to be a pyramidal shape because in one of the orbitals a lone pair is present. So lone pair bond pair repulsion is going to be more than bond pair repulsion, and hence the angles, they are going to be closer, and hence we find that the shape has distorted from the normal tetrahedral one to a pyramidal shape. So you can look over here, we have the ammonia molecule, we have the phosphine molecule. This is going to be NH3, this is PH3. Now importantly over here you can see that we have the bond angle to be 107 degrees, we have the bond angle in case of phosphine to be 94 degrees. So there are differences also in the structure of these hydrides. So let us talk more about these differences in the structure of the group 15 hydrides. So one difference you've already seen in the structure of the hydrides of the group 15 elements is going to be related to their bond angle. But I will just now come to it. First of all, let us talk about the bond lengths. So what are we going to see in the bond lengths of the group 15 hydrides? Well, I'll show you just the values first of all. So the nitrogen-hydrogen bond in case of ammonia is going to be 101.7 picometer. In case of phosphine, it is going to be 141.9 picometer. In arsenic hydride, it is 151.9 picometer. And in stibbium hydride, please do remember antimony, the Latin name is stibbium. Okay, so we call that as stibbium hydride. It is going to be 170.7 170.7 picometer, a tongue twister for me. Okay. So what is happening? The bond lengths, they are increasing down the group. Now, why are they increasing down the group? That is very simple, that as we are going to go down the group, the size of the central atom is increasing. Therefore, the bond length will also increase. So what is going to be the trend? Down the group, as the central atom size is increasing, also the bond length is going to increase for the hydrides. Okay. So now let us quickly talk about the bond angles in the hydrides. So we've already discussed that in ammonia we have one lone pair of electron and we have three bonded pair of electrons. When all the four are bonded pair of electrons, the bond angle has to be 109.5 degrees. So this is all that we have understood from the lectures on chemical bonding, the valence bond theory, the VSEPR theory, the hybridization concepts. So in case you have any doubts related to that, you can watch our detailed lectures on chemical bonding and remove all the doubts that are going to be in your mind. Okay, so now we have one lone pair of electron and three bonded pair of electrons. Therefore, the angle decreases and it is going to be less than 109 degrees 28 minutes or 109 degrees 109.5 degree, because the lone pair bond pair repulsion is going to be more than the bonded pair repulsion. All right, and therefore the bonded pairs, they are going to come closer and the bond angle is going to decrease. Now what happens as we are going to go down the group? Well, the bond angles, they are going to decrease. Let me show you the value also. In ammonia, we have the angle to be 107.8 degrees. In phosphine, it is 93.6 degrees, then 91.8, then 91.3 and 90.3. So all of these, they are approximately near to 90 degree, whereas in case of ammonia, what you are seeing is 107.8 degree, and the bond angle values, they are decreasing down the group, right? So now why are they decreasing down the group? Because as we're going to go down the group, the size of the central atom is going to increase. The electronegativity of the central atom is decreasing. So the bonded pairs, they can relatively move away from the lone pair and come closer to each other. Because now they have space, the repulsion between the bonded pair of electrons is going to be less. So they will be coming closer to one another, and to minimize the repulsion from the lone pair, they will be moving away from the lone pair. So moving away from the lone pair, coming closer to one another, because the interelectronic repulsions, they are decreasing. Okay, so as we are going to go down the group, the bond angles of the hydrides, they are going to decrease. So the next, now what you can look over here, these are the bond dissociation energy values. So we are going to talk about the bond dissociation energy in case of hydrides. So looking at the values, you can tell that the bond dissociation energy of the hydrides, this is decreasing down the group. We have it maximum for ammonia and it is least for antimony hydride. Bismuth hydride, the values, they were not known, so I have not written them down. Okay. So what does this mean? This means that the nitrogen-hydrogen bond is the strongest, and as we are going to go down the group, this bond strength, this is decreasing, because what is bond dissociation energy? This is the energy which is going to be required to break the bond. More is going to be the energy. This means more is going to be the strength of the bond. All right, so the nitrogen hydrogen bond, this is the strongest. Now why is this the strongest? Because again, when we are going to go down the group, the size of the central atom, this is going to increase. Therefore the bond length is going to increase, and as the bond length increases, the strength of the bond is going to decrease, and hence we will be having less energy required to break the bond. Okay, so as we are going to go down the group, the bond dissociation enthalpy values, they are decreasing, and the bond strength also, if somebody asks you, that is also decreasing. Okay. Now, before moving further, there is one question related to the bond angles, which I found it to be very important to discuss with you people. So let us look at the question. The question says the hydrogen, nitrogen, hydrogen angle in ammonia is 107.8 degrees, while in the case of phosphorus, the hydrogen phosphorus hydrogen angle in phosphine, this is 93.5 degrees. This is the values we have just now seen. Relative to phosphine, the P character of the lone pair in ammonia is expected to be less, more, same, cannot be predicted. And this is a question which was asked for the West Bengal JEE 2019. So what is being asked to you is, what is the P character of the lone pair? Now, how will you tell this? This is what I wanted to talk about with you people. And the very easy way in which you can talk about is going to be the Dragos rule. Although Dragos rule is a part of the Benz rule, and Benz rule also is going to explain it, but I found it much more easier to explain it to you with the help of the Dragos rule. If you want to have an understanding of the Benz rule, that is also again available in my lectures of chemical bonding. So you can have an understanding of the Benz rule also. That will also help you understand the same concept, that what is going to be the P character of the lone pair, what is going to be the P character of the bonded pair. So everything you can understand over there as well. But I will answer this question with the help of the Dragos rule. So what is Dragos rule? The Dragos rule says that if the central atom of the molecule is a third row or a third period element or below in the periodic table, the lone pair will occupy a stereochemically inactive s orbital, and the bonding is going to take place through p orbitals. So what does this mean in terms of the group 15 hydrides? What this means is that if we have a group 15 hydride from phosphorus and beyond, because phosphorus is going to be third period element and beyond, then the lone pair is going to be in the s orbital, and bonding will take place through the p orbital. So if I write down the electronic configuration of phosphorus, this was 3s2 and 3p3, right? So it is going to be in the s orbital that the lone pair is present, and the bonding is going to be taking place through the 3p orbitals. So what this means is that here no hybridization is taking place, whereas in case of ammonia, the s and the p orbitals, they were undergoing hybridization and producing 4 equivalent orbitals of the sp3 type, right? But here hybridization is essentially not taking place. Another important thing which the Dragos rule says is that if the electronegativity of the surrounding element is going to be less than 2.5 or equal to 2.5 also, then the bond angles, they are going to be nearly 90 degrees. So this is what we again see in the case of the hydrides also. So if you look at the bond angles, we see that in case of ammonia, the bond angle is 107.8. Going on to phosphine, which we explained by the understanding of that the lone pair bond pair repulsion is going to be more than the bond pair repulsion, that the bond angle values, they decrease. But then from phosphine to arsenic hydride, then from antimony hydride, bismuth hydride, why are these values not changing drastically? Why all of them, they are almost equal to 90 degree? Well, this is what the answer is. The Dragos rule explains us why these angles, they are close to 90 degree. All right. So this is one thing that we have answered with the help of the Dragos rule, and the other is now related to the question that we have. So let us answer the question also. So from the Dragos rule, what do we infer? We infer that in case of ammonia, hybridization will be taking place, whereas in case of phosphine and below group 15 hydrides, hybridization will not be taking place. So if I want to write down the electronic configuration of phosphorus and nitrogen just before bond formation with the hydrogen atoms is taking place, I can write that in case of phosphorus, it will be 3s2 3p3 because no hybridization is taking place. Whereas in case of ammonia, we will be seeing that nitrogen atom will be undergoing hybridization. So we will be having 4 equivalent sp3 hybrid orbitals, right? So now if we want to write down the s and the p character of the lone pair and the bonded pair of electrons, it will be easy for us, right? In case of ammonia, we will be having nitrogen undergoing hybridization. So we will be having all of them for to be sp3 hybridized, which means that either it is lone pair or a bonded pair of orbitals, we will be having 25% s character and 75% p character, right? So in case of ammonia, lone pair S character will be 25%, lone pair P character will be 75. Even the bonded pair S character will be 25 and the bonded pair P character will be 75%. No problems. In case of phosphorus, we see that the lone pair is going to be present 100% in the s orbital. So lone pair S character is 100% and P character will be 0%, and all the bonding orbitals will be P character only, right? So bond pair S character will be 0% and bond pair P character will be 100%. Clear? Okay. So from this, what do we infer? From this, what we can infer is that if we want to talk about the S character of the bonding orbitals, what is the S character? This one. So for the S character of the bonding orbitals, as there is going to be a decrease in the bond angle, the S character is also decreasing. And what about the P character? The P character is increasing. And then if we want to talk about the lone pair of electron orbitals, so in that case, the S character is going to increase and the P character is going to decrease with a decrease in the bond angle. Okay, now I hope this is clear and we can now answer easily our question. So now what is going to be the correct answer for this question? What we are asked is the P character of the lone pair in ammonia relative to phosphine. So in case of ammonia, the lone pair is present in the sp3 hybrid orbital, whereas in case of phosphine, it is present in the s orbital, right? So here it will be 75% P character, here it will be 0% P character. Therefore, we will be having the P character of the lone pair in ammonia to be more. So the correct answer is going to be B choice. So the next we have is the formation of hydrides, and the first way in which we can make these hydrides is the action of water on dilute mineral acids on nitrides, phosphides, etc. So for example, we have magnesium nitride. When this will be reacting with water, we will be getting magnesium hydroxide, and along with that ammonia is going to be evolved. We will be learning a lot many reactions for the preparation of ammonia when we will be discussing ammonia separately as a topic. Okay, and similarly we have calcium phosphide. When this will be reacting with water, we will be getting calcium hydroxide, and along with that phosphine. Again, phosphine, more preparatory reactions we will be learning separately as a lecture when we will be talking about phosphorus compounds. Okay, then we have zinc arsenide reacting with a dilute mineral acid like HCl. It will be forming zinc chloride, and along with that arsenic hydride, which we call as arsine, is going to be produced. And then we have magnesium stibide, along with that reacting with HCl. So magnesium chloride is produced and stibine is produced. So this is what stibium hydride or antimony hydride. And then we have again magnesium bismuthide reacting with HCl to produce bismuthine. Along with that, magnesium chloride will be produced. Okay, so I hope these reactions are easy, not difficult ones. So the next way in which we can produce these hydrides is by the reduction of the trichlorides. So all the trichlorides of group 15 elements except bismuth, please do remember, will be giving us the corresponding hydride on reduction either with zinc acid or with lithium aluminium hydride, which is a very strong reducing agent, right? So we have the group 15 metal to be standing as M. So the trichloride of these group 15 element, then they will be reacting, for example, with lithium aluminium hydride. What we will be getting is the corresponding hydride of the group 15 element, along with that lithium chloride, and along with that aluminium hydride will be produced. One more important thing that you can remember is along with the MH3 type of hydrides, nitrogen can also form hydrides like hydrazine, which we discussed in the oxidation states also, N2H4, and also it will be forming hydrozoic acid N3H. where we will be having the azide ion, that is N3 negative. So we will be having 3 nitrogen atoms with 1 negative charge. This is called as the azide ion. Okay, and this hydrozoic acid, this is very important in organic chemistry reactions. And then hydrazine, this is prepared by oxidizing ammonia with sodium hypochlorite, that is NaOCl. So ammonia, when it will be reacting with NaOCl, we will be getting hydrazine along with at NaCl, and water will be produced. Now this hydrazine is also a very strong reducing agent, and hydrazine and its derivatives, they are used as rocket fuels. So again, you will be studying more about hydrazine and hydrozoic acid in the various reactions in case of organic chemistry. Next, we talk about the characteristics of these hydrides, and first is that these hydrides, they are covalent compounds. So here you all know that the oxidation state of the group 15 element is going to be -3, right? So either this -3 oxidation state can be by the gaining of 3 electrons, or it can be by the formation of a covalent bond, by the sharing of electrons. So we see that the gaining of 3 electrons is thermodynamically not feasible. Therefore, it is going to be showing the -3 oxidation state only in the covalent compounds. It is not going to be gaining electrons. It is going to be sharing electrons, right? So it will be covalent compounds as far as the group 15 hydrides, they are concerned. And then due to the electronegativity difference of the group 15 elements and hydrogen, we will be seeing that these are going to be polar covalent compounds. And going down the group, we know that the electronegativity difference is going to reduce. Therefore, the polar character of these bonds is also going to reduce. So the next we are going to discuss the boiling and the melting points. First of all, look at the values. Please remember, wherever I am showing you the values, this is just for your understanding. You do not have to remember these values. Only the trends, they are important for you people to remember. Okay. So here, first of all, let us discuss the boiling point. So for the boiling points, what you can see is that ammonia, this has a boiling point of 238.5 Kelvin. Going on to phosphine, the temperature has fallen. From phosphine to arsenic hydride to antimony hydride to bismuth hydride, the temperatures, they are constantly increasing. And for bismuth hydride, the boiling point, this is the highest of all the group 15 hydrides. So this is what is going to be important for you people. Okay, so what do we understand is that from phosphine to bismuth hydride, the temperatures, they are constantly increasing. Why? Because as the molecular weight is going to increase, the van der Waals forces of attraction, they are increasing, and because the intermolecular forces of attraction, they are more, so we will have to supply a greater temperature to break the bonds, to break these intermolecular forces and convert a liquid into a gas. Right, so boiling point is conversion of a liquid into a gas. Therefore, we see that as the molecular weight is increasing, the van der Waals forces of attraction, they are increasing, and the boiling points, they are increasing. But then why in the case of ammonia, which was having the least molecular mass, the boiling point is high? Well, that is because of the intermolecular hydrogen bonding. So we know from all the intermolecular forces of attraction, hydrogen bonding, this is the strongest of them all. So wherever intermolecular hydrogen bonding is going to be present, we see a higher boiling point. Okay, so what will you remember over here as a order? We will be having the order as bismuth hydride, the highest boiling point. Then we will be having ammonia. Then we will be having antimony hydride, arsenic hydride, and least of all is going to be the boiling point of phosphine. So how will you remember it? From phosphine to bismuth hydride, the temperatures, they are increasing, and here you have to put in between ammonia. Okay. So next we have is the melting point, and the trend essentially is going to be the same. We do not have the value for bismuth hydride, so we can see the compare the melting points of the rest of the group 15 hydrides. Again, ammonia, this will be having a higher melting point of 195.2 Kelvin, and from phosphine to antimony hydride, again you can see that the melting points, they are increasing. Okay, so we are again having from phosphine to antimony hydride, the melting points, they are increasing. Why they are increasing? Because the molecular weight is increasing, the van der Waals forces of attraction, they are increasing. So to convert a solid into a liquid, again the temperature required is going to be more. But again, then why in case of ammonia we have a higher melting point? That is because of intermolecular hydrogen bonding. Okay, so I hope this is clear. Essentially, if you are leaving out bismuth hydride, you will be seeing the same trend for the boiling and the melting point. Okay. So this is going to be the order of the melting points. Highest is going to be or ammonia. Then it is going to be the lowest for phosphine again. Okay. So this is what you can remember is as a table also, that ammonia, this will be having a higher boiling point, then it will be going far low to phosphine, and from phosphine again it starts increasing. I've just not put over here bismuth hydride, which will be going even above ammonia, because this way if you just remember this, you will be remembering the boiling point as well as the melting points also. Okay, and here you can see over here the hydrogen bonding in case of ammonia. Nitrogen, this is electronegative element as compared to hydrogen, so this will be having a partial negative charge, this will be having a partial positive charge. The next molecule, hydrogen, will be also having a partial positive charge, and nitrogen, this will be attracting it. Okay, so this is what we know as the hydrogen bond. So next we have is the basic strength. So all of you know now that all these group 15 hydrides, they have a presence of lone pair of electrons on the central atom, which they can donate. And because they can donate a lone pair of electrons, so they will be acting as Lewis bases, and the elements which can take these electrons, accept these electrons, they are Lewis acids. So they are going to donate this lone pair of electrons to the electron deficient compounds, Lewis acids. All right. So now the tendency to act as the lowest basis, they is going to decrease down the group, or you can say that the basic character is going to decrease down the group. We will be seeing that ammonia, this is going to be strongly basic, phosphine, this is going to be weakly basic, and the rest of the three, they are going to be very weakly basic, or you can say hardly they will be having a basic character. Okay, now why is this so? Let us understand that. So you all now know that nitrogen, this is the smallest of the group 15 elements, and as we are going to go down the group, the size of the central atom is going to increase. So the hydrides of nitrogen, they have the smallest size. The lone pair which will be present on nitrogen, this will be concentrated on a small area of the central atom, and therefore it will be having a maximum electron density, and hence the electron donating capability is going to be more. But when we are going to go down the group, if you talk about bismuth, this will be having a largest size, right? So the lone pair will be concentrated on a much larger area. So it is going to be hardly any electron density on the central atom. Therefore, the electron donating capability is also going to be negligible. Okay. So the next we talk about thermal stability. So what do we mean by thermal stability? The stability on heating. How much is it going to be stable when we are going to heat these compounds? So what do we find? That as we are going to go down the group, the thermal stability is going to decrease such that ammonia will be most thermally stable, and going down the group, bismuth hydride, this will be the least stable. Again, why can you people think of now? That we have the size of the central atom increasing down the group, and the tendency to form a stable covalent bond with a small hydrogen atom is going to decrease. So a small atom is going to be stable with a small atom, or otherwise you can understand that in case of nitrogen, hydrogen, this bond length is going to be small. In case of bismuth hydride, because the size of bismuth is more, so this bond length is going to be more. And that is what we have studied, that the bond strength for the small bond is going to be more. The bond strength of bismuth hydride bond is going to be less. So the bond dissociation enthalpy is going to be more for nitrogen hydrogen bond, and the bond dissociation enthalpy for the bismuth hydrogen bond is less. So this bond, this can be broken very easily, and therefore what does that mean? The bond strength is less, and if the bond strength is less, this means that the thermal stability is also going to decrease down the group. Okay. Now next we have is the reducing character. Reducing character means that these are going to act as good reducing agents, or they should have a good property of getting oxidized themselves, right? So oxidation in terms of oxygen means gain of oxygen, or it can mean loss of hydrogen, or it can mean loss of electrons, right? So this is what do we mean by oxidation reaction, and these substances which can get oxidized, they will be getting acting as good reducing agent. So what do we want in case of the hydrides? What we want in case of the hydride is the loss of hydrogen, right? So the loss of hydrogen is going to be maximum where the bond is going to be the least stable, so that the bond can be easily broken and the hydrogen can be released from the compound. Okay, so what do we find is that the reducing character, this increases down the group from ammonia to bismuth hydride. The reducing character is increasing. So why is it increasing? Now you understand. Greater is going to be the instability of the hydride, greater is going to be the reducing capability of the hydride, because when the hydride is going to be less stable, we will be seeing that the bond will be breaking easily. So bismuth hydride, this bond is the least stable, we have just now studied. So this can be broken up very easily, and this will be reducing hydrogen. And the loss of hydrogen is going to mean it is going to act as a good reducing agent. Okay. Now, please do remember that in case of ammonia, this is not a good reducing agent. This is the top of the group 15 element hydride. But even then, it can reduce copper oxide to copper at a high temperature. So copper oxide plus ammonia will be forming copper, nitrogen, and along with that, water will be released. Okay, so I hope you will remember this very important thing. So the next we have is solubility now. So solubility, you all know that like dissolves like. So water is a polar covalent molecule and ammonia is also a polar covalent molecule. Therefore, they both can make hydrogen bonding well with each other, and hence ammonia is going to be the maximum soluble. As we are going to go down the group, the electronegativity of the central atom, that will be decreasing, and as it is going to decrease, the capability of forming hydrogen bonds is going to decrease. The polarity of the covalent bond, that is decreasing, hence the solubility in water is also going to decrease. So now this is the end of today's learning part, and now it is going to be testing time, when I am going to be asking you a few lecture review questions. All the questions I have answered them in the lecture, and therefore I want you now to look at these questions and answer them in the comment section. Only the students who will be answering me back will be getting the correct answers. So question number 1 is, which of the following forms p pi bonding? So it is either going to be phosphorus, or it will be arsenic, nitrogen, or antimony in their elemental state. Which one is going to be showing p pi bonding? That is what you have to tell. The next we have is phosphorus is more reactive than nitrogen. Why? First of all, we have the choice to be electronegativity of phosphorus is low. Ionization energy of phosphorus is low. The phosphorus single bond is weaker than the nitrogen triple bond, and phosphorus bond is polybaric. So again, this I have already explained you. You have to choose the correct option. Question number 3. The best reducing agent among the following is ammonia, arsenic hydride, phosphine, and antimony hydride. The next question, which of one of the following is the strongest base? Again, we have talked about the basic strength also, and the choices, they are ammonia, arsenic hydride, phosphine, and antimony hydride. And this is a question which was asked for the IIT entrance exam way back in 1989. But these are important questions, and they will keep on coming up again and again. Now the last question, this is a JEE Advanced 2018 question. We have not discussed all the 4 choices over here, but we have discussed 2 choices. First, let me read down this question for you. Based on the compounds of group 15 elements, the correct statements are correct. Okay, so you have to choose more than one correct answer over here. So bismuth oxide is more basic than nitrogen oxide in the 5th oxidation state. NF3 is more covalent than bismuth fluoride. Then we have pH 3 boils at a lower temperature than ammonia, and the nitrogen single bond is stronger than the phosphorus single bond. So you will be able to attempt choices number C and D today. You will not be able to attempt A and B choices, because this is related to the oxides of the group 15 elements, and this is related to the halides of the group 15 elements, which are going to be my next 2 lectures for you people. So you will be able to answer this question in totality after 2 more lectures, but you can at least tell me which out of these 2 choices, they are correct. C or D. C is correct, D is correct, or both of them they are correct. You have to give me an answer. This is a JEE Advanced 2018 question. Okay. So this is going to be the homework for you people. The 5 questions, you have to put your answers in the comment section. So that would be all for this lecture. I hope you've enjoyed your learning with me. I have tried my level best to give you each and every explanation to small bit of topics which can be asked in the examination. There should be no question left unattempted by you people. There should be no question which you have not understood the theory with me. So that is what my motive is. So I hope you are enjoying your learning with me and you are looking forward to the next lecture where we are going to now have again a detailed discussion on the group 15 oxides. Okay, and then it will be the group 15 halides that we will be talking about. So see you again in the next lecture. Bye bye.